Section: Introduction. In this section, we introduce the design methodology of FocusLLM. First, we explain how we build FocusLLM on the architecture of large language models, LLMs, to enable it to manage very long text contexts. Then, we outline the training process for FocusLLM. Regarding the architecture, we note that the standard model has a complexity that increases quadratically with the sequence length, which limits its ability to work with longer texts. FocusLLM is specifically designed to overcome these limitations. The framework of FocusLLM is straightforward. Each decoder shares the same model, such as LLMA2. For each chunk of text, we enhance the original decoder with a small set of additional parameters. In terms of notations, we consider a long sequence with a certain number of tokens. We divide these tokens into memory tokens and local tokens, ensuring that the local tokens do not exceed the model's default context length. We also break the memory into chunks, each of which is sized to fit within the context length. We define the original decoder model and its hidden dimension. When processing the memory, we add a small set of new parameters to allow the model to generate candidate tokens. These candidate tokens help indicate whether a chunk contains relevant information and assist in predicting the next token based on the current chunk. Section Summary. In this section, we introduce FocusLLM, a framework designed to enable large language models to effectively handle extremely long text contexts by utilizing parallel decoding and a minimal number of additional trainable parameters. Our approach maintains low perplexity and enhances performance on downstream tasks, demonstrating significant improvements over existing methods for processing long sequences. Section: Local Context Injection. In this section, we introduce our FocusLLM, which aims to share the task of understanding long texts across smaller segments. Instead of using memory tokens stored as cache like previous methods, we add a small set of local tokens, which we call the prompt, to each segment. This allows us to decode each segment in parallel, making it easier to manage long sequences by concentrating on the most relevant parts while still keeping the overall context needed for accurate decoding. We define this process by stating that each segment is updated with local tokens, where the number of local tokens added is determined by a hyperparameter. To minimize computational load, we don't need to use all local tokens. For example, if the local context is 2000 tokens long, we might only use 512 tokens or a brief instruction. In our experiments, we typically use 512 tokens for inference, which captures the essential local context. Next, we explain our approach to parallel decoding. Instead of predicting the next token one at a time, we generate potential tokens from different segments simultaneously and then combine these to produce the final token. This method differs from earlier encoding techniques, which often involve storing context in a memory format for later use. While previous methods, like CEPE, also break long texts into segments, our FocusLLM focuses on decoding within each segment. In our framework, encoding transforms text into hidden states for future use, while decoding generates the next token based on the current text. We view our method as a type of implicit decoding, as we aim to keep track of the next token based on the current segment without explicitly mapping hidden states to vocabulary tokens. To maintain the original model's generalizability, we only introduce a new set of trainable parameters to the linear projection matrices at each layer. We denote the modified decoder model as F_dec. Through parallel decoding, we derive one candidate token from each segment, which includes key-value hidden states from the last token in each layer. The output of the candidate token in the self-attention module is calculated using the new parameters, where we process the input hidden states of the candidate token and combine them with the representations of normal tokens. Finally, we concatenate the generated candidate tokens with the local tokens and process them through a fixed decoder. We also design two loss functions for optimizing the candidate tokens. Importantly, the process of obtaining candidate tokens from each segment is independent, allowing us to perform parallel processing, which is why we call it parallel decoding. Section Summary. In this section, we introduce FocusLLM, which enhances the processing of long texts by appending local tokens to each chunk and employing parallel decoding to generate candidate tokens, rather than relying on traditional encoding methods. This approach allows us to efficiently manage long sequences while maintaining essential global information, ultimately optimizing the token generation process through independent, parallel operations across chunks. Section: Efficiency. In this section, we discuss the efficiency of FocusLLM. Our parallel decoding method significantly lowers the computational demands compared to standard architectures. When handling long sequences, the main challenge in the transformer model is the attention mechanism, which has a complexity that grows with the square of the sequence length. By splitting the sequence into smaller chunks, we reduce the complexity within each chunk. This allows us to process these chunks simultaneously, leading to a much lower time complexity. The space complexity also decreases, allowing FocusLLM to operate with a fraction of the original computational load, specifically 1 over the number of chunks. Our experiments show that as sequence lengths increase, the efficiency gains become more pronounced. To ensure our method is generalizable and fair in comparisons, we used the same training data as activation beacon, with sequences ranging from 3,000 to 8,000 tokens. We utilized 70,000 samples from the Red Pajama dataset and 10,000 from Long Alpaca. Red Pajama is an open-source dataset for Llama 1, while Long Alpaca is designed for instruction following tasks. We provide detailed statistics of our training data in a table. For our experiments, we focused on the Llama 2-7B chat model. After adding the parameters discussed earlier, we found that the total additional parameters were around 2 billion. We trained the model using an auto-regressive method, where the model predicts the next token based on the context from each chunk. The loss function we used only applies to local tokens, which are positioned after memory tokens. To enhance the model's ability to retrieve information from memory, we also made local tokens a part of the memory tokens. We designed 2 loss functions for training: the continuation loss, which helps the model generate new tokens based on context, and the repetition loss, which trains the model to repeat information when it is clear from the context. To ensure our model is adaptable to different chunk sizes and numbers of candidate tokens, we kept a consistent local context size of 2048 while randomly selecting chunk sizes from a predefined set during training. In the following experiments, we will evaluate the effectiveness of FocusLLM across language modeling and various downstream tasks. We aligned most of our experimental settings with those of Activation Beacon for consistency. Our training took place on a Linux server with 8 A100 GPUs, each with 40 GB of memory. We trained for 10,000 steps, equivalent to 1 epoch, using a batch size of 8 and a learning rate of 5E5. To optimize GPU memory usage, we employed a specific optimization technique. The training process lasted about 20 hours. During training, we randomly selected chunk sizes from our predefined set, and for the tokens injected into each chunk, we set a default of 512 tokens, ensuring this did not exceed the chunk size. Thus, the length of injected tokens was the smaller of 512 or the chunk size. Section Summary. In this section, we demonstrate that FocusLLM's parallel decoding mechanism significantly reduces computational complexity by dividing long sequences into chunks, allowing for a time complexity of O(L)n squared and a space complexity of O(L)(n), where n is the number of chunks. We also detail our training methodology, datasets, and experimental setup to ensure the model's generalizability and efficiency across various tasks. Section: Long Context Language Modeling. In this section, we evaluate the core abilities of FocusLLM on long context language modeling benchmarks, with text lengths ranging from 4,000 to 128,000 tokens. We assess 3 datasets: PG19, ProofPile, and CodeParrot, which include 100 long test cases related to books, archive papers, and code repositories. We compare our results with baseline models. Since FocusLLM generates text using the last decoder, we calculate the perplexity based on the last 256 tokens of each sequence. For the 128,000 token length, we filter out documents longer than this and evaluate only 10 samples due to limited data and computational costs. FocusLLM is built on Llama 2 to 7B, chat, so all comparison models are also 7 billion parameters. The baseline models fall into three categories. 1. Methods that modify positional encoding, like positional interpolation and streaming LLM. 2. Fine-tuned methods for long inputs, such as LONGALPACA16K and LONGCHAT32K. And 3. Models designed for long contexts, including AUTOCOMPRESSOR6K and Long Llama. For example, Activation Beacon compresses long texts by using fewer tokens to represent information. Our analysis reveals several key points. 1. FocusLLM outperforms the basic Llama 2 to 7B model and some fine-tuning free methods, showing lower perplexity as context length increases, indicating effective use of longer information. 2. We observe a slight increase in perplexity at longer lengths on code parrot, likely due to more evenly distributed output probabilities as candidate tokens increase, but this does not hinder downstream task effectiveness. 3. FocusLLM performs comparably to fine-tuned full attention methods while being more efficient in training. For instance, Long Llama uses 7 billion tokens for fine-tuning, while FocusLLM uses only 1/10 of that with fewer parameters. 4. FocusLLM maintains language modeling capabilities at much longer lengths than other models, achieving stable perplexity at 400,000 tokens, which is a significant increase from the original Llama 2 to 7B context length. Although models like Streaming LLM and Activation Beacon can achieve lower perplexity through token compression, they struggle to recover previous context information, limiting their effectiveness in downstream tasks. In summary, FocusLLM provides comparable performance on shorter sequences with minimal training costs while effectively handling much longer texts. By utilizing parallel decoding, FocusLLM avoids the information loss common in compression models. We will detail downstream task performance in the following sections. For downstream tasks, we select two widely used datasets, LongBench and InfinityBench. LongBench evaluates various tasks, including question answering and summarization, with average and 95th percentile lengths of 12,800 and 31,000 tokens, respectively. InfinityBench tests understanding and reasoning over extremely long contexts, with average and 95th percentile lengths of 145,100 and 214,000 tokens. We believe these benchmarks effectively reflect our model's capabilities. For LongBench evaluations, we use a local context size of 3,500 tokens for FocusLLM, in line with the official settings. Our goal is to enable LLMs with limited context lengths to understand very long sequences at minimal cost. Thus, we compare FocusLLM with the previously mentioned baseline models and recent models designed for processing extremely long inputs. Specifically, Streaming LLM uses a sliding window. INFLLM stores processed context in memory, Activation Beacon compresses preceding text, and CEPE processes long inputs in chunks. The experimental results show that FocusLLM outperforms all baseline models, achieving the best results on both LongBench and InfinityBench. This highlights FocusLLM's ability to understand and reason effectively over long sequences. We note that different baseline models have various limitations. Training free models like positional interpolation and NTK struggle with performance at 128,000 tokens due to a lack of full context understanding. Models using sliding windows or condensing techniques, such as Streaming LLM and Activation Beacon, perform poorly on InfinityBench, with some tasks nearing zero performance. Fine-tuned models like LongChat and CEPE also face limitations with supported lengths, particularly CEPE beyond 128,000 tokens. While methods for length extrapolation and continual training can scale context length, they incur high computational and memory costs, risking GPU memory limits. In contrast, FocusLLM processes text in chunks and employs parallel decoding, conserving memory and time during inference. Overall, FocusLLM demonstrates superior performance across various downstream tasks at the same parameter scale and can be deployed with limited resources. Section Summary. In this section, we evaluate FocusLLM's performance on long-context language modeling using datasets with text lengths from 4K to 128K tokens, demonstrating its superior capabilities compared to baseline models while maintaining efficiency in training and processing. Our results indicate that FocusLLM excels in understanding and reasoning over long sequences, achieving the best outcomes on both shorter and extremely long benchmarks, while effectively managing memory and computational resources. Section: Further Exploration. In this section, we explore FocusLLM further. First, we examine the maximum sequence lengths that FocusLLM can effectively manage. Next, we analyze several important parameters quantitatively. Finally, we conduct ablation studies on the training loss functions to understand their effects on the model's performance. We believe that FocusLLM can handle very long sequences. To test this, we perform experiments on the passkey retrieval task. The results show that FocusLLM achieves nearly 100% effectiveness at lengths up to 400,000 tokens, surpassing all other models. We also extended our language modeling experiments to 400,000 tokens, a length where most models struggle. The results confirm that FocusLLM performs exceptionally well in both passkey retrieval and language modeling tasks at this length, highlighting its effectiveness and versatility in real-world applications. Regarding memory usage and inference time, we compare FocusLLM with previous long-context methods that retain global information by keeping a cache of all context. We focus on models like Standard, Pi, NTK, Long Llama, and CEPE. Our findings indicate that while serial processing is sufficient for memory and inference time, parallel processing is more efficient when memory resources are ample. Although FocusLLM splits long texts into chunks, it still outperforms other long context methods despite a slightly longer inference time. We also investigate how different chunk sizes affect performance. Larger chunk sizes are generally better, as they require fewer forward passes, but smaller sizes may allow for more precise processing. In our experiments with a total sequence length of 8,000 tokens, we test various chunk sizes and find that perplexity remains stable, supporting our hypothesis that larger chunk sizes can be used effectively with models that have longer default context lengths. Next, we examine whether a larger local context size improves performance for FocusLLM. Our results show that reducing the local context size from 3,500 to 1,000 tokens leads to a slight decline in performance for most tasks, except for the passkey retrieval task, which benefits from clear instructions. This suggests that a larger local context size provides better local information. Finally, we use both continuation loss and repetition loss in training FocusLLM to enhance its natural language modeling and global information recovery capabilities. Our ablation studies reveal that while continuation loss alone can handle some tasks, it struggles with those that depend heavily on prior context. Similarly, repetition loss ensures accurate restatement but lacks generalizability for generating new tokens. Thus, using both loss functions together is essential for improving FocusLLM's performance and generalizability. Section Summary. In this section, we explore the capabilities of FocusLLM, demonstrating its ability to handle sequences up to 400K tokens effectively, outperforming other models in both passkey retrieval and language modeling tasks. We also analyze the impact of chunk sizes and local context sizes on performance, revealing that larger local contexts improve results, and highlight the importance of using both continuation loss and repetition loss for optimal model performance. Section: Related Work. In this section, we discuss related work on long context language models. We have observed that recent advancements in this area have led to new methods aimed at overcoming the limitations of transformer architectures. One approach involves length extrapolation in transformers, where techniques like positional interpolation help models handle longer sequences. However, these methods often struggle with distractions from noisy content in extended texts. Another area of research focuses on modifying the attention mechanism or using compression techniques to keep long texts manageable. For example, some studies have shown that using sync tokens with a sliding window can produce smoother outputs, while others have dramatically expanded context through compression. Yet, a common issue with these methods is their inability to utilize information from all tokens effectively. We also note that integrating memory layers into transformer architectures has become a key strategy for improving long context understanding. Memory-enhanced models typically use recurrent strategies to iteratively incorporate information from the current window into a lasting memory. Alternatively, some methods encode the entire long text into memory tokens, which can then be queried for relevant information. For instance, one approach uses a small encoder to sequentially encode long text segments and then integrates these into a decoder. However, these methods face challenges, as the memory length does not scale well, and increasing memory size can lead to high computational costs. In contrast, FocusLLM demonstrates better training efficiency and remains effective with very long texts.